the pen testing portion now. All right, so with that kind of understanding of some of the concepts of web application security in browsers, now I want to talk about how we, and I'll say we when I refer to attackers because I want us all to put the attacker hat on and think like attackers. So how we as attackers will look for vulnerabilities in web applications. You had a great question about protocols that are in use, and HTTP is the main protocol, right? WebSockets do exist, but HTTP is like the main protocol of the web. And at the end of the day, it's HTTP everywhere. Modern web apps can seem crazy complicated with like tons of convoluted JavaScript and all these hot new frameworks, whatever you're using on the reactive client side rendering, and like 18 megabyte JavaScript files that get downloaded and ran. But at the end of the day, every web application is it's just a client talking to a server over HTTP. So client would be a Firefox, right? Server would be some web server in the cloud. At the end of the day, all it is just a bunch of back and forth, right? Sending a GET request for HTML, giving a response. Sending a GET request for some JavaScript, getting a response. Sending a GET request for a meme, getting a response. And so testing web applications is always going to be just a matter of reading, sending, and modifying HTTP. So as manual testers, we want to be able to send our own HTTP. We want to be able to like tamper with HTTP. So how can we do that? Well, I showed that screenshot earlier. If we really wanted to, we could just actually write our own HTTP by hand and send it, to an open TCP connection. But a much better way, and what we'll use, is a proxy. So a proxy just sits in the middle of a client and a server and forwards traffic and responses back and forth. And this icon here is for a security proxy called Burp Suite, which we'll use in the labs. And what Burp Suite does, or what any proxy does, is the browser, the client, thinks it's talking to the server, but it's really just talking to the proxy. The server thinks it's talking to the client, but it's really just talking to the proxy. And the proxy just sits there and forwards messages and responses back and forth. So you send your GET request, the proxy forwards it on. The response comes back, the proxy forwards it on. But the proxy actually lets us pause, modify, and change things before they make that next hop left or right. So Burp Suite and OWASP Zap are security-focused web proxies. They have a lot of really great features specifically for security. But really what they just let us do is view, pause, and modify the traffic. So the vast majority of web application attacks are really just based on sending unexpected HTTP requests to a server that doesn't know how to handle them. So visually, this is web app security in a nutshell right here. A client sends a quote unquote good normal request. We catch it in our proxy. We modify it into a bad request. And the server doesn't know how to respond and just comes back with like, WTF, I don't know what to do with this. That WTF response is really what security testers live for. Like if we can coerce the server into giving us a WTF response, we might have a security vulnerability there because the server is not prepared to handle that. If you're thinking, you might be thinking like, what about SSL and TLS, right? Like the web has these security mechanisms in place that should prevent us from even eavesdropping on any traffic. And if you're thinking that way, you're totally right. Good TLS is exactly designed to prevent this, right? You should be able to know that we're talking only to the server and only the server in the browser. It's fully encrypted end to end. But as testers, we're testing our own traffic with our own browser. So we can actually configure our browser and our proxy to disable TLS for us. And that's what we're going to do. And that's how we do testing of HTTPS applications. We can configure our proxy and our browser such that it's encrypted between the client and the proxy, and it's encrypted between the proxy and the server, but inside the proxy, it's fully decrypted for us. And then we can view our HTTPS traffic in plain text and get around HTTPS or TLS traffic. So I talked about WTF responses. It all boils down to the golden rule of web security. And this is my golden rule. That's my name. It's my quote. But the golden rule of web application security is never, ever, under any circumstance, not even for a second, ever even consider trusting user input. if every web application was designed with this golden rule of security in mind, there'd be no web security vulnerabilities. You have to design your web applications to handle the unexpected. You can never ever assume that the only traffic and only data you're going to get on your web application is exactly what you would expect to get. And if you do assume that quote unquote happy path, then you'll be very unhappy when it's not taken. So all web vulnerabilities kind of boil down to applications that were developed, not taking into consideration weird things that get sent to them. So with that in mind, I'm going to jump into the first of the vulnerabilities I want to do a kind of a deep dive into. And this is a really, really big pest on the internet, cross-site scripting. Who's heard of cross-site scripting? A couple of hands I think I saw. So yeah, cross-site scripting has been around as long as JavaScript has been around. And cross-site scripting occurs when an attacker is able to force a victim's browser to execute JavaScript within a trusted origin. Cross-site scripting is a terrible name for this vulnerability. And I've been pushing for it, and there's like movements within OWASP to even just rename it because it confuses people more than it helps. What you should really think about with cross-site scripting is it's not about cross anything, it's about injecting content. A better name that we kind of refer to it sometimes is content injection. And what this does is if we know now that we understand the same origin policy, we completely bypass the same origin policy because we execute JavaScript in an origin we shouldn't have access to. So visually, it kind of looks like this. We know that same origin policy will prevent me as an attacker from hosting malicious JavaScript and accessing resources that are associated with chase.com. And I'm picking on chase.com because I bank with them and think it's funny. But they're actually really secure, so don't take this in any insider knowledge that I know Chase is insecure. They do a great job. So as an attacker, I cannot do this, right? Same origin policy prevents my JavaScript from talking to chase.com resources. So when we say a cross-site scripting attack, what we really mean is that our malicious JavaScript is smuggled inside HTTP response so that it executes over here on the right instead of over here on the left. So what does this look like? As an attacker, I might send something to chase.com. Chase.com will then load HTML, CSS in my victim's browser. And that JavaScript, because it started over here, but it kind of worked its way through chase.com and was smuggled in a response from chase.com, got loaded in the victim's browser. The browser thinks that this JavaScript here came from chase.com when it really came from me, but I just kind of bounced it through chase.com in order to load it in the victim's origin. And now my malicious JavaScript is executing inside this box on the right instead of this box on the left, and the same origin policy no longer applies. And my malicious JavaScript would have access to Chase's cookies, the storage, the APIs, anything I wanted to within my victim's browser.
So does it ever go to the Chase server, or does it just piggyback through?
Yeah, great question. So yeah, this is the magical portion right here that I glossed over, but I'll talk specifically about what this actually looks like, because there's a few different techniques to make this happen. But in concept, this is what happens: is like the JavaScript came from chase.com, or so the browser thinks. Oh, this JavaScript came from Chase. I'll execute it. I'll give it all the permissions to talk with Chase within my session. So yeah, there's three main types of cross-site scripting. These are the techniques to actually do that reflection or do that bouncing off. In a reflected cross-site scripting attack, the attacker is able to load JavaScript from the trusted origin by reflecting it up and back. And so this is just like a mirror, like it bounces and then it comes right back. And usually this is done through me as an attacker sending a malicious link to an individual to click. So I might say, hey, click this link, chase.com/XSS. My payload is embedded inside the link. The user clicks the link. That payload gets sent to the server and then gets reflected back. And so the server just replays what was sent to me, or what was sent to the server, and it sends back the content, but it also sends back my malicious payload. So that's called reflected cross-site scripting, and that's what I think you were getting at, is that's one way that we can kind of just get data, boom, up and back. We kind of just use the server or our target as like a trampoline to send code and have the code come right back to us, and it executes in the victim's browser, and we have cross-site scripting. The other way is called stored cross-site scripting. This is a bit actually much more dangerous because instead of like the trampoline, we actually can store malicious code on the server. Let's say that there's a persistent field, like on, you can add a comment to a post or something like that. I can type in comments and then other users can see it. If I can embed bad JavaScript or bad content in that comment, it actually gets saved in the database. And then anyone who goes and visits that page, chase.com is essentially now serving up malicious code from its own database that I injected there. And anyone who visits that server, request chase.com, that malicious JavaScript comes back and executes within their browser. So this is called stored cross-site scripting or persistent cross-site scripting. It's a more dangerous attack because it doesn't require me to like target a particular user and say, hey, click this link. It affects any user who visits the page. And we're hosting our bad or malicious content on the server itself, and the server is just happily serving it up because it doesn't know any different. And the third type of cross-site scripting is a bit more difficult to understand, but becoming much more prevalent. And this is called DOM-based cross-site scripting. And this, in a DOM-based cross-site scripting attack, the attacker is able to load JavaScript by passing it in to dynamic JavaScript that's already loaded and executed. So visually what this looks like is we actually can take the server out of the equation kind of, because we're abusing legitimate JavaScript code that was already loaded from the server. So visually it kind of looks like this. Let's say that chase.com is serving up like a big React application all bundled into app.js. This is legitimate code. The victim visits it, the legitimate code downloads, and it's executing. And your browser is constantly executing this JavaScript, and it's trusted. In a DOM-based cross-site scripting attack, we're able to inject our XSS payload into that already running code. So the user could click on a link, and somehow, the running legitimate JavaScript, we hijack control of it, or we inject into the legitimate JavaScript, and now we have content injection and control over the JavaScript that's already running. So visually, I think you can kind of see it's different because it doesn't go to the server, it goes directly into what's already been loaded from the server. These are really, really tricky to spot and tricky to exploit, but they can really be bad news when they're discovered because the server doesn't even need to really play a part in this role at all. It's a vulnerability that exists explicitly in the React or whatever the framework is, the JavaScript application that's running. Does that make sense? Yeah, don't feel too bad. DOM-based cross-site scripting is still something that testers struggle with wrapping their head around. There's some crazy like exploit chains that have come out against this, but basically this is the main idea: is we're injecting something into already running JavaScript code.
Is that technically an injection vulnerability?
Oh, good question. Technically, yeah, I guess you could. I'm saying that we're injecting it into JavaScript code, so it is a JavaScript. But when we talk about the OWASP top 10, like #1 being injection, they're referring to server-side injection. So this is like client-side injection, and so it's a different type of vulnerability than server-side injection. But yeah, in principle, it kind of is the same because we're injecting something bad and it's executing.
This is hilarious because back in 2005 or somewhere around that time when MySpace was really popular, everyone kind of did it without knowing it, but on their profile, they would go, like, people would figure out how to like place a script tag that would do some animations or whatever, do something cool on their profile. You could go into your profile and in like your bio section where you would submit your form, you could inject JavaScript into the page so when someone visited your profile, it would run that JavaScript, which when you look at it, it's just terrible idea from the beginning. But that was pretty hilarious because I remember doing that and not even knowing like, this is bad.
Yeah. Yeah, it's funny you mentioned that. I think, did I even, sorry, I thought I had a slide, or I'd mentioned MySpace before, because yeah, that was, I guess maybe the early days of like JavaScript and the web before people like knew why this was bad. And yeah, like sites used to just allow it as a feature. And then, but by allowing it as a feature, they were pretty much violating like what the browsers had already built into security. Like the browsers had defined the same origin policy because they were worried about this. But then sites like MySpace or web apps would say, "Ah, well, we don't need that. We'll just let users run whatever they want." So like, why is this bad? Hopefully you can grasp, given the background that I've talked about the same origin policy, like why executing JavaScript, untrusted JavaScript in an origin is bad, right? What pen testers do a lot, and you'll see this in like bug bounty reports or like screenshots, is an alert box. They just use alert 1, and an alert box pops up with 1 in there. Obviously, that doesn't mean anything. That's not bad in and of itself. All this is just a very visual way to spot that we have JavaScript execution. And so as a pen tester, if I get alert 1, I usually stop. But that doesn't mean that that's all I can do. It just means that I've proved that I can execute any JavaScript. If I can execute alert 1, I can execute anything. I call that out because if you see that, or a scanner comes back and shows this, it's not like, oh, that's annoying, they can pop an alert box. This is just saying, no, I can pop an alert box, I can do anything. But there's, you mentioned MySpace. Did you ever hear of the Sammy worm? Does anyone remember MySpace actually crashed and went down in like 2005 because of the Sammy worm? There was a guy, he's an ethical hacker named Sammy Kamkar, and he did that in MySpace. He was able to embed a JavaScript in his MySpace profile that whenever anyone visited his page, they added him as a friend and then replicated that JavaScript into their page. So then anyone who visited their page added Sammy as a friend and replicated that into their page. So it became a worm that actually spread to every page that was visited. I'll try to post a link in the Slack or something when I pull it up. But I think within 24 hours, Sammy had more friends than anyone in the world on MySpace. He had like millions of friends. The worm had propagated through like all of MySpace. Every single user was infected, and it crashed MySpace. And MySpace went offline for like a day or something to fix this vulnerability. And so that was a cross-site scripting worm, or a cross-site scripting vulnerability that spread like wildfire across MySpace back in like 2005, I think it was. So yeah, what can we do? Like, we already know that we basically bypass same origin policy. So all of that worst case scenario stuff I was saying earlier is now possible. If we have malicious JavaScript, we have full control over everything within chase.com. We can change what gets rendered on the page. We can hijack links. We can serve up malware. We can steal cookies and session data. We can call additional APIs. Basically, you're infected. That's kind of how I think of cross-site scripting. Is if you're a victim and you click on a page or a cross-site scripting link, your browser is infected with this virus that can take total control and do whatever you want. So in summary, cross-site scripting is really just content injection. We're injecting malicious content and executing it. And since it comes from the good origin, the browser doesn't know any better, and so same origin policy doesn't apply. And it's extremely powerful and bad news when cross-site scripting is discovered in a big site like MySpace, or if there was cross-site scripting in Chase, that would be big news. So how do we mitigate that, right? As developers, it's our responsibility to make sure like our apps are not vulnerable. So since cross-site scripting is all about injecting content into the DOM, the golden rule applies. Never ever insert untrusted data into the DOM directly. Don't trust any data, and don't ever just like reflect it or do anything with it and insert it into the DOM without taking some precautions. So some of the precautions we can take are validation, sanitization, or encoding. Validation means we should reject input that we don't expect. If you are expecting a form to submit a zip code and someone submits 500 characters of JavaScript, that's clearly not a zip code. We should just flat out reject it, right? Don't try to parse something if you know what to expect. If you expect 5 digits of a zip code, reject anything that's not 5 digits. Sanitization is cleaning up the data, because we can't always just validate, right? If there's a comment or a free text field, they should be able to put whatever they want in there, but we need to clean it up. So cleaning it up means let's remove things like special characters, because the DOM, you'd have to inject special characters like script tags or other things that are valid. If we just remove all the special characters and just get left with plain text, we're okay. And then the final thing is output encoding. And this is, I should have put an asterisk on because this is the one that only really matters, or it's the best one to do, which is escape or encode all the special characters. So if you want someone to be able to type in like a open bracket character, instead of just stripping it, what we can also do is encode it. And if we encode that open bracket character in HTML encoding, it will get rendered on the screen and look like an open bracket character, but it won't actually be interpreted as an open bracket character. And that's what encoding is, and that's why encoding is the best defense. So you can do it both server side and client side. Fortunately, most frameworks do server side encoding for you automatically. I know you all are using Django. Django by default, if you're doing any of like the templates in Django and like rendering the HTML server side, Django will automatically escape these things for you. Here's the encoding, right? Open or less than is converted to that, single quotes, double quotes, ampersands, like these are escaped and encoded automatically for you. Be very careful with Django or any framework because they do offer ways to not do that. And if you're not using that or calling out, you know, like putting, I think in Django, the keyword is safe. You have to say like, this is safe, and then Django won't escape it. Think twice before you do that. Make sure it really is safe and that you're trusting it before you disable this auto escaping. On the client side, within JavaScript, never write directly to the DOM untrusted content, right? Avoid using .inner HTML, which will just inject HTML for you. Inner text will actually escape it for you. There's an awesome JavaScript framework or JavaScript project called DOM Purify, which you can include. It's just installed with NPM. And if you just call DOM Purify on any string, it will automatically take care of all the escaping and everything you need. So you should do that if you're ever actually injecting something you got from users. You run it through DOM Purify and you're safe. And then client-side frameworks also do this automatically for you. So I don't know how far you all are with React yet, but if you're using like hooks and data binding, this is perfectly safe within React. If we have a component called myComponent and we take a prop called myData and we do variable expansion with the curly brackets for myData, React takes care of, it does all these security checks for us and encodes this. So myData is perfectly secure to put here. But if we disabled that or did something, you know, more hacky, we might have a problem. So just rely on what's exposed to you in the client-side framework, and a lot of times, like you will be safe. Actually, I love it in React. I was playing around, and to like disable this, React, I think the method call is called dangerously set HTML or dangerously set inner HTML. So I love that the framework is like making me type the word dangerous, because you really should be thinking twice, like this is dangerous if I'm actually setting something without encoding it. Cool. Any questions on cross-site scripting?
Ronnie, could you go over what DOM Purify was again?
Yeah. Oh, you can't see that. Anyways, if you click on it, so DOM Purify is an NPM package. It's a JavaScript package. So you can install, you know, NPM install DOM Purify, and then you can require it in your JavaScript code. And it exposes some methods. I think the method is just called DOM Purify. So if you were to give it a string like HTML content, like script source equals blah, 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 and you run it through the DOM Purify method, it will return a string that's perfectly safe to put in a browser that won't actually execute anything. So it's just a helper method or a helper library to like safely encode, sanitize, and prepare any data before you put it into the browser.
Okay, got it.
Yep. So you don't need to use DOM Purify if all you're doing, like in React, is this data binding. But if you're using something besides React, or you're using React with like the dangerously set inner HTML, you can require DOM Purify in your React code, and then just call the DOM Purify function on the variable before you do anything with it, and you'll be safe.
Okay.
And worth calling out, like these are not perfect, but they are close to perfect. So every now and then, like someone will discover a way to bypass DOM Purify and they'll publish it, or they'll figure out a way to bypass like breakout of React and publish it. Those are huge deals. And React or DOM Purify will issue like public vulnerability warnings and make you upgrade. So you always should upgrade and update, but those are few and far between. And so, you shouldn't worry about that. You should just use them and make sure they're up to date.
Hey, Ronnie, I had a quick question.
Yeah.
Just as more of an aside, because it's so commonly understood that setting inner HTML is dangerous, do you know of any, is there any good use case for that, or is there always a better way to go about doing something?
My gut would be like, no, there's always a better way. But there's a million edge cases, I'm sure, in which that is required. One of the beauties of JavaScript as a language is it's really hacky, and JavaScript developers are some of the most like creative people I've seen when I've looked at some JavaScript code. And so, if something's not doing exactly what they want, they'll make it do what they want, right? And there are, ways that you could use inner HTML legitimately, but you wouldn't want to ever use inner HTML on something that like a user ultimately controlled. So you'd never use like inner HTML on like a username field or something like that. But if you're using inner HTML and you know that this data is coming from a very trusted source and it's not tampered with and it's legitimate HTML, there might be a case to actually just write raw HTML into the DOM.
That makes sense. Thanks.
Yep. Good questions. All right, so that's cross-site scripting. The next vuln I'm going to talk about is CSRF, or cross-site request forgery. So CSRF, you can kind of think of it as another bypass of the same origin policy. So as we know, same origin policy attacker in origin B should not be able to write anything to origin A. But there's two big notable exceptions when it comes to same origin policy, and those are HTML requests and cookies. And CSRF chains both of those together to bypass the same origin policy. Because same origin policy only applies to JavaScript, if we can make HTML send a request, same origin policy does not apply. And because HTML requests that come from the browser automatically include your cookies, we can abuse HTML and cookies to actually perform some actions in an origin that we don't control. And that is CSRF kind of in a nutshell. Couple things on CSRF, and then I'll talk more about it and explain that a little more. CSRF requires some sort of state changing request. So CSRF is about writing data. It's not about reading or stealing data. It's about performing an action. So we need something that changes a request, like a post that performs an action. It also relies fully on cookies. If your app is not using cookies, you don't need to worry about CSRF. And it requires some user interaction. And it abuses the fact that HTTP is stateless and browsers send cookies automatically. So here's what this looks like. In a CSRF attack, an attacker would send a link to a victim and say, hey, click this link. And it's hosted on attacker.com. And so the victim would click the link, and this is my attacker-controlled server. I will send them some malicious HTML. And this CSRF HTML will then turn around and perform a post request to chase.com. And because this is HTML and not JavaScript, the browser will send the cookies. So if the user's already logged into chase.com and has a valid session cookie, this post request that was actually triggered from here kind of bounced through the user's browser and performed an action on chase.com. Does that make sense? And because HTTP is stateless and the browser doesn't know any better, the browser sees legitimate cookies from this post request and thinks it's legitimate and that the user really wanted to do that action. And so the browser parses it and processes it. So it looks like an example CSRF attack would just look like this. It's just HTML, and usually it's done through forms. And so we would load this bad form into a user's browser, and we're going to post, it to like chase.com/account/transfer, because this is the action that's actually going to transfer money from one account to another. And we'll have some values in here, like we'll post it, we'll send it to Ropnop, and we'll send him $1,000. And then this JavaScript here, all it does is when the page loads, this post is automatically sent. So the post will get automatically sent. The post will automatically include cookies. And if the server is misconfigured, the server will think this is legitimate post action and will actually send Ropnop $1,000. So this is an example. If I were to hit this, and I send a post to account/transfer, here's what the attacker controlled down here to Ropnop $1,000. This top red box is entirely automatically set by the browser. The browser set all of these automatically for us because that's what browsers do with cookies. They send all of these cookies automatically. So an attacker doesn't need your cookie. They can just use your cookie by sending an HTML request.
So in Django, when we were making forms, we typically use the CSRF token. So
Awesome.
that's to verify that the form came from the same source, right?
Exactly. Yep. So that is the traditional defense right there against CSRF. If you don't have that, the browser never knows. It just has to assume that if it got a post request, it came from a legitimate form. Django and frameworks use these quote unquote synchronizer tokens. And what the synchronizer token is a random value that gets embedded into each form, and the server remembers what values it sent before. So when you send a form back to the server, it needs to see that random value and know that it had sent it previously. And that way the server knows that this form request came from a form that I'd sent previously. In a normal CSRF attack, you're kind of getting the request coming in without ever sending the form out. So you synchronize like what goes out with what comes in. And that's what synchronizer tokens do. And that's what Django has built in, or frameworks can take care of that automatically. So frameworks like Django make that really easy. You have to make sure that you have that turned on. If you're building something from scratch without a framework, you have to be really careful and implement something like yourself. But there's two other methods that I'll talk about for doing this without synchronizer tokens. Because same origin policy is really powerful, we can use same origin policy to our advantage, but same origin policy only applies on JavaScript. So the solution is to use a little JavaScript because the browsers treat that more securely than they do HTML. So the two approaches are, you'll hear double submit cookies or custom headers. So in a double submit cookie, what we are doing is the form is actually not pure HTML. The form is kicking off some JavaScript. So in this case, this would be a legitimate HTML form for like chase.com or to like transfer some credits. And if we were to when we submit the form, we actually execute some JavaScript. So onClick executes JavaScript instead of just sending the HTML. And the JavaScript will read a cookie value and then append the cookie value to the form. And why does this work? This works because of same origin policy. This JavaScript can only ever execute within the origin that the form was loaded. So if we loaded a malicious form from ropnop.com, the JavaScript wouldn't be able to access the chase cookie called CSRF token. So we know now that the form had to have been loaded from chase.com, and therefore we can trust that that form request is legitimate. That's how a double submit cookie can use. By sprinkling a little JavaScript in there, we can verify and we can trust that this form only came from some trusted origin and not some random attacker hosted web server. And when the server gets the response, all it needs to do is just verify that a cookie value and a post value match, that these two values match. If they do, then the server knows that JavaScript sent this and that JavaScript could only be executed from my trusted origin, so I can trust this request, and I'll parse this credit response. And most client-side frameworks, I'm not sure about React, sorry, but I know like Angular, like can be configured to just always do this for you. So if you're ever sending a form through Angular, like Angular, if you have a cookie called XSRF token, will just automatically take care of that for you. So again, really nice to just leverage like these mature frameworks that have these security mechanisms built in already. The other option, again, using JavaScript, is just add a custom header. For security reasons, JavaScript is the only way that you can send custom headers on HTTP. So if you have a custom header that gets sent, say a header called XSRF token, you know that that request came from JavaScript. There's no way in a browser with HTML to send any non-standard header. So a really easy way to check if a form is legitimate or not is, does it have a custom header? So on a server, we might just say, hey, does this header exist, like XSRF token? It can be named whatever, it just has to be non-standard. If a non-standard header exists, then JavaScript sent this form. And if JavaScript sent this form, the only way it could do that is if it was loaded from the same origin because of same origin policy. So therefore, we know that this form is legitimate and we should process it. If we don't have this custom header, we should not do anything and we should ignore it.
Ronnie, is this when you start getting into API tokens? Because that's what I've been thinking. So if I've got a React single page application, the form may never really been truly generated by the server. It's all done in JavaScript. So in order for me to do this via an API securely, I've got to have some kind of custom header and a token. Is that the idea here?
Yep. Yeah. So basically, this custom header only tells the server that this form is legitimate. But it doesn't actually, there's not enough information in this header alone to say like the user is logged in and authenticated. So in this case, we're still using a session ID cookie that says I've already logged in and I am user XYZ. So in combination, we're now handling authentication, authorization, and CSRF protection with the custom header. But for APIs, you're 100% right. We could actually wrap all of that up into a single header. So, you'll see an authorization header get sent in client-side frameworks a lot. The authorization header could be like authorization bearer and then a bunch of, values, maybe like a JWT. And the server can make the determination that we're authenticated, we're authorized, and this is not CSRF, all from one header. So yeah, you can combine them all into one header, and that's what like an API token would do exactly. So kind of in summary, CSRF, it did drop out of the OWASP top 10, like I mentioned, and the reason it is no longer in the top 10, like we don't see it as often as we used to, is precisely because JavaScript has risen, right? Like as JavaScript and single page applications and APIs get more popular, CSRF gets less popular, because CSRF is just not possible if we're talking JavaScript and we're talking like REST APIs and we're sending JSON. CSRF only exists within HTML, forms, and cookies. So it's good if you are designing in your application and all it's doing is talking to the API over JavaScript, you don't even need to worry about CSRF. But if you're building a like traditional web application in Django where you're sending forms and then they're clicking it and like the form responses are coming back and you're not really using JavaScript in there, you have to be aware of CSRF and make sure that you have that synchronizer token set or that you are using JavaScript in some way. Make sense? This is very dense information. I know I'm throwing at you and like condensing it in here. My goal is to kind of make everyone at least familiar with it, but this will come with practice. This will come with when you start like testing web applications yourself or writing frameworks and seeing like how CSRF gets done. But these slides will be yours as well. So these are definitely like good references, hopefully for you in the future as well, to refer back into like, what were the ways that you can prevent CSRF? Oh yeah, in concept, this is how it looks.
And this all assumes there's no underlying vulnerability in the JavaScript engine, which I'm assuming is why Google pays so much for it.
Yeah, great point. This is actually such a good question to think about. And I ask this question when I interview security engineers. And the question goes like this. If you have an application that has, and you've identified both cross-site scripting and cross-site request forgery, which one is more important to fix first? And it's a really hard question. That's why I asked like this is an interview question, but it shows if you can answer the question correctly, you kind of understand how browsers work. The answer is cross-site scripting. Because if you have a vulnerability in JavaScript, nothing you do to try to prevent cross-site request forgery will work. Because all of the cross-site request forgery defenses are based on JavaScript. So CSRF is sort of like underneath cross-site scripting. If you have cross-site scripting, you're never going to solve CSRF. If you have cross-site scripting, CSRF is always 100% possible. So you need to make sure, yeah, to your point, that JavaScript is clean, that you don't have any JavaScript vulnerabilities. Once you have that done, then you can actually remediate cross-site request forgery. Good question. Okay, the next one jumping into is injection attacks, which is #1 on the OWASP top 10. And like I mentioned earlier, when we talk injection attacks, we're now switching gears and talking server side. CSRF and cross-site scripting are client-side vulnerabilities. Now we're jumping into server-side vulnerabilities. And again, it follows the golden rule, or you must follow the golden rule. Server-side vulnerabilities target when servers handle unexpected or untrusted input. And injection is sort of a catch-all, and there's subcategories of injection. So SQL injection is very common. You probably may have heard of it. Command injection, server-side template injection. Whatever you're injecting into the server side falls under this category of injection vulnerability, but at its core, it's all about the server mishandling untrusted data. So injection usually occurs when a server takes input and quote-unquote translates it. And we talked about protocols earlier. When there's protocol translation or protocol transition, you have to be very, very careful. So let's say our server's talking with MySQL, right? And this is a very common use case for Django. You've got like a MySQL backend. Django is sort of this like middle layer on the server. It has to take in HTTP and then it has to execute SQL. And those are two distinct protocols. So some sort of translation has to happen on the server side, right? It has to take HTTP and create SQL from it. So if I send a post request to my Django server, and my username is ropnop, and then I need to look up the users of the table in a database that are associated with the username ropnop, I'll take this HTTP parameter and I'll create a SQL statement from it. And SQL might look like this: select star from users where username equals ropnop. So we've taken an HTTP variable and we've created SQL from it. This is where you have to be very, very careful. This is where injection attacks can occur. Because if we take untrusted user input and construct the commands, really bad things can happen. So what happens if I send my username and I send ropnop single quote space or space 1 = 1 semicolon dash dash? This is a classic like SQL injection attack. If we take this whole string in red right here, ropnop, and we drop it inside these quotes right here where username equals ropnop, our SQL statement actually becomes something totally different than we wanted it to be. We have select star from users where username equals ropnop, which is what we sent, but then this single quote here gets put right here, which actually closes the where parameter, and then the rest of our HTTP becomes valid SQL, or 1 = 1, and then colon, slash, slash, or dash, dash, which is a comment symbol in SQL. So what does this SQL do when we execute it?
Gives you all the users' information?
Exactly. So yeah, this SQL, now instead of just pulling out where our username is ropnop, because we have an or in here and 1 = 1 is true, it's always true. So basically anything that's or true just becomes true. We're actually dumping every single user and not just ropnop. This is classic. This is what SQL injection looks like in theory here, is by sending some special characters, the server mistranslates it and executes bad SQL, and we can control the actual SQL that gets executed against the database. And so we can pull out users that are not us, or we can pull out data from other tables that are not us. So SQL injection lets you escape this normal SQL query and inject additional SQL after it. Sometimes we really need to be creative in crafting these, and SQL injection can get really complicated. You have to kind of like think and understand valid SQL syntax. But generally, because we are injecting into the where clause in a SQL statement, we can't just execute like another select command. We have to add on to that. And SQL has things like union and join. And I'm not sure if you guys have used SQL before, or have used it much in your web development, but you can construct very complicated SQL queries that return data that you should not be able to see. And there's a great tool called SQL Map that is like the gold standard of automatically exploiting this for you. SQL Map will construct some of these crazy complicated SQL queries that you'd never want to write yourself. Here you can kind of see like under payload what some of these look like, right? Like ID equals 1 and select 7857 from select count star concat hex values, select rand 02 information group by XA. Like it gets very complicated, but that's valid SQL. And when that runs, you're extracting other data from the database that you shouldn't be able to see. So how do we mitigate that? Can't stress it enough, so I'll say it again. Never ever trust user input. Do not ever take valid, or take user input directly. And just like how I said in cross-site scripting, never take user input and directly write it to the DOM. Never take user input and directly execute SQL, or never take user input and directly run a command. You have to think about it. You have to escape it. You have to make it safe. So some popular methods: escape everything. And what I mean by escape is like if you put a backslash in front of special characters, SQL ignores them. So you could put a backslash in front of everything, and that would get you a lot of the way there in protecting against it. There's certain like stored procedures that exist on SQL that make this safe. They're like functions essentially within SQL that take care of this for you. But the best way, and really the only way that you all need to be thinking about, is just don't write SQL and use object relational mappers, or ORMs. If you're using Django, you are using an ORM. Django wraps SQL commands into like an API and exposes functions that let you do things without having to write your own SQL. So if you ever find yourself writing raw SQL, seriously reconsider what you're doing. It's probably not the best way to do it. This top right here is some Python. This is basically executing raw SQL and constructing a string with format. Bad. This is ripe for SQL injection. The better approach is this is Django syntax, right? If you have a user object or a user data model, right? User.objects.filter name equals username. Django takes this, it will construct some SQL, but it's going to construct it in a very safe way that's not possible to do SQL injection. So rely on the framework. Don't write raw SQL. If you're talking with a database, use what's exposed to you. If you do have to write raw SQL, make sure you're escaping it and really handling it very, very carefully. Make sense?
Yep.
You'd think with the rise of these frameworks and the rise of things like Django and Express and client-side frameworks that we'd hopefully see a decrease in this. But if history has shown us with the OWASP top 10, injection has been #1 for as long as it's existed, and it's going to probably be #1 next year when the new one comes out. This is very, very common. Even though, in my opinion, it's like fairly easy to fix or remediate. This goes to, are there ever any legitimate use cases? Probably not in this case for writing like raw SQL, but it's easier. And unfortunately, just a lot of developers hit a problem they need to solve, and they can just write some raw SQL and they populate a variable in there and they run it. And we still see this a lot all the time. All right, the last thing I'm going to talk about before the lab is cross-origin resource sharing, or CORS. I think we mentioned this already. Have some of you heard of CORS before, or maybe seen CORS errors come up when you're like programming with APIs or using S3 buckets? CORS is not a vulnerability. This is a feature, but I want to call it out because it can be misconfigured. So like I talked about, same origin policy is very powerful and by default very restrictive. But there are plenty of legitimate use cases for loosening the same origin policy. Like we can't always assume that we're only ever talking within our origin. Like the web isn't built that way. The web, you have to talk to different websites and different APIs. So the browsers implemented cross-origin resource sharing, CORS. And this is not a vulnerability, it's a feature. But you really have to think twice every time you deliberately loosen same origin policy or start implementing CORS, that you're not doing it in a way that over opens it up and disables some of the security features. So these are the official browser headers that correlate with CORS. So you probably have seen these before. If you looked at headers or read documentation, access control allow origin, methods, headers, credentials. When you use CORS, it is entirely up to the server, the provider, to determine how consumers should use it. So these headers are set on the server that you are exposing. If you are writing an API that you want to expose, you are responsible for setting these yourself if you want non-origin requests to work. Where CORS gets confusing is there's some cases where CORS applies and there's some cases where CORS doesn't apply. And the browsers call these simple requests and pre-flight requests. Simple requests, the browser just considers safe out of the box, and so it doesn't really apply many checks to them. Simple requests are things like fetching an image or reading some data, like fetching a plain text data or fetching plain text image or something. It's usually only GET requests, and there's no credentials. And so these are public open APIs that you can just like request, and there's no credentials involved. The browser will automatically send those for you, but it will not return the response to the page unless CORS allows it. The other category are called pre-flight requests. These are considered dangerous requests. These are anything that does require credentials, anything that's private, anything that's a state-changing operation, writing data, not just reading data. The browser takes some additional precautions, and I'll show what that looks like. So here's a real-world example. I'm picking on Chase again. This is a response from Chase's analytics API that I see all the time when I'm browsing chase.com. The analytics server responds with these 4 access controls headers. And these are basically saying, the server is saying to the world, I'm only ever going to even entertain requests that are either post, get, or options by the methods. I'm only ever even going to entertain requests that come from www.chase.com, from this origin. I will allow you to send your credentials, but I'm only going to allow these very specific headers to come in. So it's sort of a whitelist approach. The server has to say, I'm only going to allow X, Y, and Z, and they chain these together to very limit what they can allow. So here's a CORS example visually. If I'm on my attacker machine and the ROPNOP origin, and I want to talk with Chase's API, and my JavaScript, I have it coded to send a request to get public accounts. This is a simple request. The browser doesn't think this is very dangerous, so the browser will go ahead and send it. The server will actually send us a response with these access control allow headers. But what's cool is the browser, you can think about it like in the sandbox, the browser actually gatekeeps the response from coming into our origin and checks to make sure the CORS headers exist before passing them on. So the request does get sent, the response does come back, the browser intercepts it, and then it compares these headers with what sent it. And in this case, the origin, only allowed origin is chase.com. The origin doesn't match, so the browser actually just denies it. For dangerous requests like posts, these trigger what's called a preflight. And a preflight uses the options header, and it's kind of just like a quick poke at the server to say, I'm about to send you something potentially dangerous. Can you make sure this is okay? So when, if my JavaScript were to send a post request, the post request would say, the browser would see that the post request is about to go out. The browser would say, whoa, hold on, this is a dangerous request. I better make sure this is cool. So the browser then automatically sends this options request. It says, hey, I'm just double checking that I should send you something before I actually do. The server is going to respond with the access control headers. The browser is going to compare those headers to what's about to get sent. And if they don't match, the browser just won't even send the post request at all. So these are, yep.
Would that just respond with like a 401 or something? Like
it would usually just be like a 200 okay. Like there wouldn't be any data in there because it's an so when you send an options request to a server, the server is only responding with headers and no body.
Okay, so it's always 200.
Yep. So the server is okay to send headers to anyone. They don't care. There's nothing sensitive in there. But it's like this it's called a pre-flight request. It's basically like a pre-security check. Like, this is about to happen. Are you cool with it? And the browser is going to respond with these headers and say, as long as this stuff matches, you can send it. And the browser says, well, that doesn't match, so I'm not going to send it. Really cool security feature built into the browsers here. Very hard for me to wrap my head around when I first started dealing with this, and I apologize if you guys are swimming right now because this course is quite complicated. But in theory and like in at a high level, this is all that's doing. The browser is sort of this middleman gatekeeper that's using CORS headers to decide what's dangerous and what's not. Where vulnerabilities arise. If you want your server to be available to anyone in the world, like your API should just be totally public, you can specify a wildcard in the origin. And that tells the browsers you can allow it from anywhere. It's a wildcard. But it should only ever be used for public and unauthenticated data. So you've explicitly designed your API to be public and you don't care who sees it, you can go ahead and use a wildcard. For data that requires credentials, this is a recipe for disaster. And thankfully, the browsers know that. These teams that develop browsers are very, very smart when it comes to security. So they explicitly forbid wildcards and credentials from coexisting. If you set these headers, the browsers just ignore them because this is too dangerous. You can't allow a public exposed API on a wildcard and allow credentials to be sent. Unfortunately, going back to what I said, where JavaScript is super hacky and developers always find creative solutions and workarounds, there is a workaround to this, and it's called dynamically setting the origin header. And my heart just drops every time I see this mentioned on Stack Overflow or a question or documentation somewhere, because this is very prevalent. Developers publishing answers on Stack Overflow or documentation and saying, oh yeah, CORS is just like a major pain in the butt to configure and get right. So what we'll do is we will just dynamically set the origin header to whatever you send us, and we'll get around CORS that way. So these like 5 lines of JavaScript here are copied and pasted from a Stack Overflow answer that basically just disable CORS entirely. And what this is doing is dynamically setting the the response header from the origin that requested it. But what this does, and this is what it looks like, if I were to send a request that had an origin of foobar1234, and the server responds and says, allow origin foobar1234, it's dynamically setting this header based on what I sent it. And don't ever do this. What this essentially does is take the entire beautiful same origin policy that the browser team spent years developing and perfecting and just throws it out the window. You disable same origin policy if you do it this way. Because now that worst case scenario I talked about, malicious JavaScript that can just talk to your, my Chase account and transfer all my money is possible because the origin's set dynamically and a wildcard, and we essentially have full read and write access to a different origin. In this case, like cross-site scripting isn't even necessary anymore. Like our JavaScript has full control over our API because we have misconfigured CORS and we've disabled same origin policy. Really, the mitigation here is just don't do that. But the mitigation more in depth is try to understand what's actually happening. Like I know as a developer, if I'm developing rapidly and prototyping, it's extremely frustrating when like my API is not working and I see in my browser that it's like blocking requests from coming back to me. And I'm like, oh, I just want this to work. But the solution is not to just disable it. The solution is to just spend a little more time, try to understand why it's not working and configure it to work in a safe manner. Okay. I don't want to just like end on that, but I wanted to follow up because I know of everything that I've talked about in this entire workshop, this is by far the most complicated. So I apologize for that. It's still, takes me a long time to wrap my head around cores. But does it kind of make sense conceptually? And are there any questions around like cores and headers when we're talking with APIs?
So it's kind of like a filter, and the browser says, "Hey, I have this," and the chase, the server, whatever, will say, "I accept this," and they pass each other, and what gets through gets through.
Yeah, you can kind of think of it like a whitelist, where when the server responds with those headers, it's basically a whitelist, and it's saying I'm only going to allow X, Y, and Z, these origins, right? And when you dynamically set it, what's happening is the whitelist goes out the window. You're not like trusting anything explicitly. You're trusting anything implicitly. So you're not filtering anything. You're just allowing anything.
So I think I'm going to end up running into this issue with the project I'm thinking about doing, Ronnie, for a senior project, because I'm looking at trying to put a Django-based API together that may also go out and get third-party APIs. And I'm kind of sensing that's where this issue comes in. So if I wanted to bring in weather or geolocation information and spit it back out in a consolidate API, is that where I have to be able to whitelist my third-party data providers? Is that the issue here? Kind of seems like a microservices issue. If I was just a monolithic API and I was the only person to give you data out of Django, it doesn't seem like it'd be a big issue. But if I've got different services I'm consuming and spitting back out, is that where this comes in?
Yeah, this definitely is way more prevalent because of microservices and multiple APIs that are hosted everywhere. But it's a great question. I can see you're thinking totally along the right lines. It's important to remember though that this is set at the provider level and not the consumer level. So if you are writing your application and you want to talk to weather.com's API, weather.com is actually the one that has to allow it. Right? You're not configuring a whitelist and saying, I'm going to allow my app to talk to weather API. Weather.com is saying, I will allow your app to talk to me. Now, this is where it goes into those like public unauthenticated APIs, because weather.com does offer a public API, and they will put a wildcard origin in there, which is fine because this is not a secret API. It's just weather data. So weather.com will have an API that has a wildcard origin set, which is their way of telling the world, go ahead and use our API, it's okay. Now, if weather.com had a private API, let's say that you create an account on weather.com and then you want to query the API for like the weather in my particular zip code or something like that, and it knows, I'm logged in, weather.com has to explicitly allow your client to use that data. So that's the difference between public data and like authenticated data or private data. If you're just using public APIs, just using public data that the server is okay with the world knowing, you should be okay. If you need to tightly integrate with Google and say, I want my app to, on behalf of a user, read their Gmail, you need to get express permission from Google, and Google has to configure their server to allow that.
Yeah, you're right. It's a lot to wrap your mind around, because then you throw in a React single page application, and I could be technically calling those APIs from the client direct to the data provider. Yeah.
Right. As long as you're only calling like public APIs, it'll work. But you'll notice, you'll definitely see it when you're developing. If you look in your web console in your Chrome browser or whatever, the browser will spit out those errors and it'll say request was blocked due to cross-origin resource sharing. That means you tried to do something that the server did not want to allow you to do, and you'll have to figure out a different way of doing it, or collaborate or coordinate with the server to configure the server to allow it. But if you're, trying to talk with weather.com's API and they're not allowing it, you're going to have a hard time probably convincing weather.com to open up their API to your React app. But there's probably a different way you could go about doing it.
Okay. Yeah.
Yeah, it gets really complicated, and there's
I'm trying to think of kind of a use case, and the simplest one is if I go out and get, let's say I just get temperature from my client, but I want to save those temperature trends into the database on the Django backend.
Mm-hmm.
Now I'm having the client potentially go fetch data from a weather API and post it back to, I don't know. Yeah, it gets weird.
Yeah. These are fun. They're fun to me. Fun might be a bad word, but these are like fun architectural discussions. The other piece to what you just said to keep in mind is that same origin policy in cores only applies on browsers. So if your browser is talking to the weather API, you need to worry about this. If your Django server is talking to the weather API and then giving the results to your React app, it's totally different. You don't need to worry about that because you can actually send secrets and authenticated materials in your Django server to talk with weather and not show those in the React app.
So how do you get to stay a pen tester and not eventually get sucked into being a system architect? That's kind of the myth.
Good question, because I'm a system architect now. No, you absolutely can. I mean, like I said in the beginning, I spent a lot of time as a pen tester just constantly breaking things, and for me personally, I kind of got old after a while. Like I was, every 2 weeks I was on like a new client project, and they'd give me a new web application, and I was seeing the same types of vulnerabilities over and over again. And I'd write it up in the report, send it to them, and then I'd come back a year later for like the yearly pen test, and I'd see the same issues again. And I was sort of like, oh, I want to just help you fix this. So that was just my mentality. I wanted to be on the fixing side, or like actually, find it and then go help them fix it. But you can certainly also just have a career, and there's nothing wrong with it. It's just me personally, but you could absolutely have a career where you're just constantly, a breaker, and not being on the fixing the architecting side. Cool, great questions, guys. I'm a little behind my anticipated schedule, but now we're finally getting into the hands-on lab portion of this. But let's take like just a 5-minute break so I can use the restroom and get some water. And then when we come back, I will stop slides and just start sharing my screen. What I'd ask is for all of you, if you haven't already, or if you can, maybe during the break, for this hands-on lab, the 2 tools that we're going to be using are Burp Suite, which I've talked about. There's a free edition of Burp Suite, the Burp Suite Community Edition. Download it, install it, whatever platform you're on, they have an app for it. And we will be using Firefox as our browser. So if you don't have Firefox installed, if you can also just install Firefox. Firefox is the easiest to configure for our purposes here, so it's just what I'm going to be using. And then I will point you at a vulnerable web app that's on the internet I created, and we can all walk through it together and start hacking it. Sound good?
Perfect. Yep.
All right. Yeah, I will be back. We'll take like 5 minutes, and if you don't have it, now's the time to install these tools and get them installed and set up, and we'll walk through the configuration in a minute.